Hello everyone and welcome to the second video of my XMOS StartKit series. In the first video I gave a brief overview of the evaluation platform and the XMOS microcontroller chip itself. If you haven't seen that, I suggest that you go and watch it first, because otherwise what I'm showing today might not make much sense. In the first part of this video I'm going to discuss how my LED strip works, how it's all wired up and how you have to drive it. And in the second part of the video I'm going to discuss the code that I'm using on the XMOS to drive the LED strip. The LED strip itself consists of several of these segments. In total there is 75 segments, and each of these segments has 3 RGB LEDs, which means that there is really 9 LEDs on there. Because one RGB LED consists of a red, a green and a blue LED. In addition, there is this chip that is this WS2811 driver chip that is sort of the core of the driving of all the LEDs. If you're wondering how this is wired up, they did pretty much what is suggested in the datasheet. This comes straight from the WS2811 datasheet. It's an interesting datasheet because the English is quite weird in there. But in any case, this is how it's all wired up. The colors are not as they're shown here. They start with green and then continue with red and end with blue. But anyway, and in addition to that, they don't have this 33 ohms series termination resistor in there. Although this resistor is just a series termination to prevent transmission line effects from propagating. So for some reason they decided that this was not necessary. What this means is that because these 3 LEDs here are in series, you can really set the color, the red, green and blue color of each segment individually. And this is on a 256 level scale, which means that you can also have kind of graduated and not that bright red and mixed color and things like that. So if I move this out of the way, as we've seen, the LED strip consists of several segments, and there is a 12-volt supply, a ground, and the data in supply. That is really where you have to stream in the data. Next, we're going to discuss the protocol that is expected by this data import. Actually, they chose quite an interesting approach to this, because you're supposed to send in the brightness levels of your LEDs as a stream. And the first segment, that is the first WS2811 chip, is going to consume the first packet that you send in and forward all remaining packets. So the second segment will not see the first packet, because that's going to be consumed by the first segment, and the first segment will then start with forwarding the second packet, which will then get consumed by the second segment, and the second segment will forward everything starting from the third packet. So that's their way of sort of distributing all the values across all LEDs in that strip. As a consequence, what you have to apply to this data import is first a reset packet, which is really just keeping the data in line low for more than 50 microseconds. And then you send the first packet, that is the packet for the first segment, the second packet, and so on. I have 75 segments, so I'm going to send 75 of these packets, and then start all over with a reset packet and my next values. If we sort of zoom in into one of these packets, we get this, which is really, we first have to send some data that relates to the first LED in the second segment, then the same for the red LED and the same for the blue LED. So really these packets consist of sort of 3 chunks, one for each LED. Remember that all the three RGB LEDs are in series, which means that whatever color we set is applied to all three of these LEDs at the same time. This also means that we just need 3 packets because there is no way to set the color differently on different RGB LEDs of the same segment. And if we zoom in to one of these LED sort of sub-packets here, what we have to send there is really an 8-bit value with the most significant bit first, so that is bit 7, bit 6, bit 5, and so on, all the way to bit 0. So in fact, these segment packets here consist of 3 LED packets, which itself consist of 8 bits each. Now the question is, how do we transmit these bits? And what you get from the datasheet is, if you want to transmit a high bit, you first have to pull the line for high for 600 nanoseconds and then pull it low for 650 nanoseconds. If you want to transmit a low bit, you only have to put the line high for 250 nanoseconds and then pull it low for 1000 nanoseconds. That's 1 microsecond. In fact, this is using the high-speed mode. You can also have these WS2811 driver chips running in sort of a low-speed mode where the timing doubles. But the way the manufacturer manufactured my particular LED strip, it's in high-speed mode, so I have to comply with the timing in this illustration here. One thing to note here is that no matter whether you're transmitting a high bit or a low bit, the total duration for that bit is always 1.25 microseconds in both cases. So the difference between the high and the low bit really is the proportion of the high pulse compared to the low pulse of the bit. In this case, it's 600 nanoseconds compared to 650 nanoseconds, so it's sort of almost the same. But in the case of the low bit, it's 250 nanoseconds compared to 1000 nanoseconds. That is the high pulse is much shorter. No matter what kind of microcontroller you're using to drive these chips, now is a good time to ask yourself how you want to meet that timing. Because to get 250 nanoseconds out of a chip, in some instances this is not that easy. For example, a bunch of people managed to pull this off on an Arduino that is clocked with 8 megahertz. And if you think about how much time you have for one CPU cycle, there is not much budget to actually to meet that timing. In addition, there is a tolerance of plus or minus 75 nanoseconds, so that's kind of short. And I didn't want to do that with an AVR, so I started this project with an FPGA where it's really easy to do this. But then when I discovered the XMOS chip, I decided that I'd gain some flexibility in changing the platform and continuing with the XMOS. So how am I going to do that on the XMOS? I am going to divide the bit, no matter whether it's a high or a low bit, into sort of 4 segments. 1, 2, 3, 4, 1, 2, 3, 4. In addition to that, I will take my 100 megahertz reference clock and divide it by 32. If I do that, each clock period is going to be 320 nanoseconds. I get this by taking my reference clock, dividing it by 32, and then inverting the whole thing to convert the frequency into period. And then, if I have these 320 nanoseconds for each clock cycle, I can come up with this scheme here. That is, for the high bit, I will transmit a high, a low, and a low. And each of these is going to be 320 nanoseconds. So when I'm transmitting 2 highs subsequently, that will be 2 times 320 nanoseconds. And that's 640 nanoseconds. While I should be transmitting really 600 nanoseconds, I have a tolerance of plus or minus 75 nanoseconds. So that would be, in the worst case, 675 nanoseconds or 525 nanoseconds. And the 640 nanoseconds I have here actually meet this timing requirement. Although you have to be a bit careful here because there will also be some clock drift and things like that, but it turns out that these requirements are met. For the low bit, if I transmit one high and 3 lows, my high is going to take 320 nanoseconds, while I should be transmitting high for 250 nanoseconds. So I'm even more off from what I really should be transmitting, but it's still within spec. And the 3 lows here, that's 3 times 320 nanoseconds, that's 960 nanoseconds, and that's again close enough to 1000 nanoseconds that I should be transmitting. So as we'll see in the code, I will really, instead of transmitting 1 high bit or 1 low bit, I will transmit 4 bits that add up to this high or low bit according to the scheme I just showed. Lastly, before we get to the code, let's talk about how my project is set up. I have a bunch of XC files. In particular, one I call WS2811 driver that talks to the LED strip port. And the LED strip port is really is this data import here that gets this whole stream of packets that I discussed in the beginning. So that will take care of doing that. In addition to that, I will have another XC file that is a button driver that really reads from the push button on the board, and whenever I push the button, it's going to tell the WS2811 driver that the button was pushed. And this allows me to sort of change the effect. What I will implement in particular is one of these Larsson scanners, which is, if you're not familiar with Knight Rider, it's the thing that runs at the front of the car, and this is implemented in this Larsson file here. So this is just going to sort of move a bright spot on the LED strip from one end to the other, and then return while there is a bit of glow when that bright pixel has passed. Anyway, when I push the button, I'm going to change the color because everybody who has watched Knight Rider knows that this really has to have a sort of a kit mode and a car mode, in which the kit mode is glowing in red and the car mode is glowing in some sort of yellow amber color. So when I push the button, it's going to tell the driver that the color has to change, and the Larsson class, or actually it's not a class, it's just a C file, will then change the color. Also, I have a pixel buffer in there that is just quite a long array that contains an 8-bit value for each of the LEDs, or for each of the LEDs on the segments of the strip. And I'm just going to pass a pointer to that buffer, to the Larsson class, where it will get filled and updated. The reason I'm doing it that way is this will allow me to implement more effects easily that will just populate that buffer. But if this buffer lives inside and this part of the code here, I can just pass around pointers and have my pixel buffer populated the way I want to. I will put all my code online in case anyone is interested. And the first file I really want to discuss is the main file that contains the main function. I have a bunch of platform includes here, and then I'm including these two other, these are header files that contain some other functions that we'll discuss next. But apart from the includes, I'm really defining one output port, and this is important. This output port is buffered. It's a 1-bit port, but it's buffered with 4 bits. This allows me to write 4 bits in there that will then get serialized automatically by the hardware, as I have discussed in the first video. In addition to that, I have an ordinary input port to which the button is connected. Important to note here is that this is a 32-bit port. And that's a bit weird, because actually you just want to use the button with that is connected to one pin. However, that's just the way the board is laid out. So I have to put special code in there to make sure that I'm really just looking at one bit of this 32-bit port. But anyway, the main function here defines an interface. This button interface here is a way of communication between the WS2811 driver and the button driver. Because when you push the button driver somehow has to tell the WS2811 driver that the button has been pushed. And this is implemented using something called interface that we'll look at in detail. After defining that interface, I've got this par block here, and again, this is not C, but this is a special XC keyword that allows me to run stuff in parallel. In particular, I'm going to run on tile 0 the WS2811 driver, and also on tile 0 the button driver, but the compiler will take care of putting each of these two tasks on different logical cores of that 0 tile. And I'm passing the port to the LED strip to the driver, as well as that interface, and I'm passing the port of the button to the button driver, again together with that interface. One thing I didn't show, because it's in one of the header files that I didn't print out, is the actual definition of that button interface. And it turns out that this is fairly straightforward. I start with the interface keyword, I give it a name, and then I just tell what kind of functions can be called. So in this case there is just a pressed function, and what is going to happen is the button driver will call that pressed function and thus notify the WS2811 driver that the button has been pressed, and this event can then be processed inside the WS2811 driver code. Let us discuss the WS2811 driver code next. Because the syntax is a bit strange if you're not familiar with XC, I'm first going to tell you what the code does, and then we'll look at how this is achieved. Remember that this part of the code is responsible for sending out the data from a buffer to the LED strip. And in fact, this will do two things. It will either wait for a timer event, that is when the next bit pattern has to be sent off to the LED strip, or it will wait for a button push, in which case it will change the mode from kit to car or vice versa. So there is a bunch of includes as before, and then I'm defining the LED count, which is the number of addressable LEDs on my string. Because I have 75 segments on the LED strip and 3 colors per segment, this is 75 multiplied by 3. Next, I'm defining this update period, which just means that every 50 milliseconds I'm going to run an update, change the bit pattern and send it off to the LED strip. To pull this off, I need a timer and a clock. So I'm defining these two. And then I have this WS2811 driver function that is what I'm really calling from the main file and assigning to a tile. As you've seen before, this receives the output part itself, that's P, as well as one end of the interface. And because this code is the end that is listening on events that are sent through the interface, this is called the server end. So I have a server interface, that's the button interface, and I call this actually button interface. Okay, the first thing I'm doing inside this code is I configure my clock. I take the LED clock and I divide it by 32. As I've discussed in the beginning. Then I tie this clock to the port P. This is actually exactly the same that what I've shown in my first video with the UART example, with the difference that in this case I'm actually starting the clock, which I forgot to do in the first video. If you don't do that, the clock is not running and then it's just not working. So this is setting up the clock and the port. Then I define this LED buffer that is an array with the number of elements that is equal to the LED count. So for each LED on my LED strip, I have an element in that array that I can set to any value between 0 and 255, because this is 8-bit elements. Then I need some stuff to actually initialize and do the update of my buffer. And I'm not going to discuss that because this is really simple code, although I will put everything online, so in case anyone wants to implement the same, maybe there will be some inspiration in my code. But it's really simple. All I'm doing in that code is I have a current index that points to wherever the bright spot is on the LED strip. And on each iteration, I either increment or decrement that index, depending in which direction I'm moving, and I set the corresponding element of my buffer to the brightest value I can have, which is 255. What I also do is I decay all the LED values, which will give this nice glowing effect. So if you're interested in how to do that, have a look at that code. But anyway, lastly, there is also this enumerator that is called Larsson mode, and this is just an enum that I can set to either kit or car, depending on which mode I want to be in. To do the whole thing, I need a timer, because I sort of have to figure out when the 50 milliseconds have elapsed. So that's the timer T that I need. The first thing I'm doing is I'm storing the current time inside a variable time. So note that there is a timer T, that's this guy here, but there is also a variable time that just keeps track of some time at which the counter will elapse. And once I've set that up, I enter this while loop that runs essentially infinitely. So let's have a look at that while loop. In this while loop, as I outlined before, I'm doing two things. I'm waiting either for the timer event here or for the button interface pressed event. This ordered clause here just tells me to, whenever the timer elapses, I want to prioritize that, because this will give me the nice 50 milliseconds refresh rate no matter what. But the timing is not so critical here, because nobody will notice if this is a couple of microseconds late. But in any case, that's just something nice to add. So let's start with this one. If the client, that is the button driver, calls the pressed function of the interface, I get this button interface pressed event, and all I'm doing there is I just, if the mode is set to kit, I set it to car, and otherwise I set it to kit. So this just kind of swaps between these two modes. You could also write this as if mode equals kit, then mode equals car, otherwise mode equals kit. So this is just some shorthand notation for that. Maybe the more tricky part is the timer business. So here I'm checking whether the timer has a value that is after whatever I have stored in my time value. And we'll actually see that in the end, this time variable here is incremented by the 50 milliseconds I defined in my define at the beginning of the file. So whenever this case is executed, the time variable is incremented to the next point in time at which this part of the code has to be entered. And this really checks whether the timer has a value that is later than what is stored in the time variable. And if that is the case, I enter these two nested loops here. The first loop just iterates through all the elements of my pixel buffer array. The inner loop iterates from 0 to 7, and that is to address each bit of the respective element inside of the pixel buffer. If that bit is high, that is 1, then I send this to the port, which is 0011. Now if you paid attention, on the first sheet I had in this video, I actually had this the other way around. I had 1100, and for the low case I had 1000. So you might wonder why this is inverted, and the reason is just that when the XMOS hardware is serializing whatever you send to the port, this is serialized with the least significant bit first. So the least significant bit in this case is 1, and that's really what you want to send out first, not the 0 over here. So this is why this is reversed. The last piece of code I want to discuss is the button driver, although quite honestly it's mostly more of the same stuff that we've seen before. As before, there is a bunch of includes, and I define a debounce delay of 10 milliseconds. This is because the push button on this board doesn't do any hardware debouncing. So essentially that means that if you push it once, this might get recorded as several events because the sort of the plates inside the button might bounce and trigger 2 events. This is why we have this kind of hold off time, which means that when you record a button push event, during the next 10 milliseconds you're just going to ignore any further events in case they appear. And this is also what makes this code a little bit more convoluted than what it actually is. By the way, this code is straight from a application node from XMOS that tells you how to do this. So there isn't much magic in this. There is one function button driver here. This is the task that is initialized in the main code and assigned to the second core of tie 0. And this first initializes a bunch of variables, current value and is stable, and then there is a timer and a debounce timeout. And we're going to see in a second what these do. Then there is a while loop, and this is really very similar to what we had before. Let me zoom out a little bit to catch the whole thing on camera here. So this runs infinitely as before, and it waits for 2 events in this select statement. The first event is when the button is pressed, and the second event is when the debounce timer has expired. So let's look at the debounce timer first. As opposed to before, this syntax is a bit different because they added something called guard, which is really an additional condition that has to be met for the code inside of the case block to be executed. So on a high level, the variable is stable is initialized with 1. When you push the button, it's set to 0, and after some delay, it's set to 1 again. And that's exactly what this code does. If isStable is false, then we wait for the debounce timeout to happen. And once the debounce timeout happens, that is after 10 milliseconds, isStable is set to true again. And if we look at the other case above, we only enter this piece of code, this block, if isStable actually is true. So when isStable is false, the only way to change something is by this debounce timeout code down here. But if isStable is true, that is, the last pushing of the button has occurred more than 10 milliseconds ago, then we enter this code of block when the value of the button port changes. And that's what happens when you push or release the button. And also the new value of the port is stored in this new val variable here. So this only checks for any events on the port. But because this is a 32-bit port and the push button is really connected to the first pin of that 32-bit port, we have to check for the pushing or releasing of the button specifically. So we take the new value and mask it with the least significant bit, because this is where the push button is connected to. And if that is false, that's 0, it means that the button is being pressed. Otherwise it would be 1, just due to the nature of how the board is laid out. So if the button is being pressed, then we send off this pressed event through the button interface. And this is what is actually waited for in the WS2811 code. There is this case button interface pressed, and this is executed when on the server side of things this code is called here. And an important thing to note is that I'm pretty confident that this is blocking. It's either blocking directly, or there is a small buffer after which it's blocking when this buffer gets full. So and this is sort of important, as we'll see later. But anyway, we send off this event here, and the rest is just to reset things. So the current value now is whatever the new value was before. Is stable is set to 0, which allows us to enter this block down here, which takes care of the debouncing delay. And the current time is stored in a variable current time, and as before, we add to the current time that we get from the timer the debounce delay, which is sort of the next trigger event to happen, and that would be making sure that we can record the next pushing of the button after the debounce delay. So that's more or less it. Now, really, there is two things left to do. First, of course, I have to show you how this thing actually runs. I'll do that at the very end of the video. But let's think about how this parallelization makes things easier. Now, in my code, I managed to sort of decouple the pushing of the button from the sending of the bit stream to the LED strip. Now think about if you were, for example, to record the pushing of the button in an interrupt service routine. That might happen at any point in time. It might also happen while you're actually already sending off the stream to the LED strip. And as we've seen, the timing is pretty critical there. So you really don't want to interrupt your byte stream transmission just to cater for the push button. But because this is actually blocking, and you can check whether this function is called or not in the client whenever you want, this is not interfering with each other. Furthermore, because I have this in an ordered nature here, really we first check whether the timer has expired, and if the timer has not yet expired, we check for the push button. So this priority list here allows you to maintain a very tight timing and a nice decoupling of user interaction, such as pushing buttons, with time-critical code, such as sending off things at the proper point in time. Great, so that's basically it for the second video. I hope that was interesting. I'm fairly new to this stuff, so maybe I misinterpreted a bunch of things, or you have something else to add. Please do so in the comments. Maybe there will be a third video later on in this series as I progress with the project. The next steps are to actually mount the LED strip to the shelf, and that's going to take some time. So I'm not really sure whether there really will be a third video, but if there is anything interesting to share, I will do so, and I thank you for watching.